Okay, looks like we're live. Get that up. We'll wait a couple of minutes. We don't officially start for 2 more minutes. Just want to make sure we're up and running. Okay. Look, there I am, coming online. Okay, looks like we're live. And let me turn off my sound. Haha. Okay. Hi to the 6 of you who are here already. We'll wait a couple of minutes until it's officially time to start, and then we'll get things underway. So we'll do a quick recap of a few review things, and I'm skipping the warm-up today. What we're going to do is basically, I've got five examples with eigenvalues planned, eigenvalues and eigenvectors. We'll see how it goes, but I'll do a couple of reminders on vectors and systems first. Okay. I'll give people a chance to tune in. All right. Hope everyone's doing okay. We've made it to the last class. It's been an interesting run. Hope you're all making it all right. Most of you are doing a pretty good job keeping on top of things. Glad to see that. By the way, I looked at the numbers for the third test, and they're actually pretty consistent with the previous 2 midterms. So most of you seem to have gone about that test honestly, despite having access to Symbolab and things like that. So that's always good to see. I'll mention that I think tomorrow, we'll see. I'll still be answering your emails and the forum posts and everything, but I might take a bit of a break tomorrow. It's very tiring. Anyway, it's time to start. We got 9 tuning in. There we go. Okay. See, we waited till the start time. We just doubled our viewership. Good. Okay, so welcome everyone. The plan for today, just kind of, I'll put this over on the side. We'll do things in OneNote, because then I get sort of infinite scrolling, which is nice. Plus I get this cool space pen. So just a couple notes. What are we going to do today? We're mostly going to do examples with eigenvalues and eigenvectors. And we'll try to remind you of a few things as we go. So we'll try to remind you of a couple things along the way. We're not going to hit on everything in the entire course. That would be pretty hard, but we'll try to hit a few. And I'm going to hope that my computer holds up for me. On Tuesday, it made it through my 1410 class just barely, and then my computer kind of died in my calculus class, and the stream ended sooner than it was meant to. So we'll see how it goes. Okay, so quick reminder on just vectors, plain old good old vectors, right? Now I'm using the matrix notation for vectors, right? So x1, x2, x3 rather than the angle bracket notation, just because we are in this context of eigenvalues and eigenvectors. We want to be able to multiply by matrices, right? So we know that we can do vectors in R2, R3. We can go to Rn if we want. We can put any number of components in there, but we mostly do R2, R3. We know how to add, right? And we'll see we need a bit of adding and stuff occasionally, right? So we know that we can add, right? We can do 2, -1, 3, +3, 0, -4, and we know we just add term by term, right? 2 + 3 is 5, -1 + 0 is -1, 3 - 4 is -1. We know that we can scale, right? We can multiply by a scalar multiple. So if I'm doing 5 times 2 - 1, 3, I do 5 times 2 is 10, 5 times -1 is -5. 5 times 3 gives me 15. We know that we can do length, right? So we know that if we wanted to take the magnitude of, so let's say if x is, say, 1, 2, -4, and I want to calculate the magnitude of x. We do square root of 1 squared plus 2 squared plus, well, you know, I usually get lazy and I just write 4 squared. Yes, it's minus 4 squared, but when you square, the negative goes away, right? And so you get something like, what's that one? 16 plus 4 plus 2, square root of 21. And then if you wanted, let's say, a unit vector. So remember, the definition of a unit vector is it's a vector with magnitude 1, right? Maybe I shouldn't use x for that. I'll call it maybe u, right? And one of the ways that you can get a unit vector, if you don't have one, is take any vector that you've got, take some vector x, and you multiply by 1 over the magnitude, right? And the reason that this works is, remember that you have this scale property, right? If you have a scalar multiple times a vector, right, then you can pull the scalar outside of the magnitude. Except if c happens to be negative, you want to account for that, so you might need an absolute value in there, right? Okay. All right. So those are some basic things that we can do with vectors. The other one I want to remind you about is we can also do, right, we can do dot products. So if I wanted to do 1, 3, minus 2, and I want to dot that with maybe 3, 1, 4, you multiply the corresponding entries, right? So we do 1 times 3, and then we add 3 times 1 minus 2 times 4, and so I get 3 plus 3 minus 8. I would get minus 2 for that dot product, right? And we had this relationship between dot product and magnitude. U dot v is length of u times the length of v times cos theta. And the other thing that we did is we did projections, projection of v onto u, right? And we said, well, the projection is given by this formula, u dot v over u dot u. And that's just a scalar, right? If our vectors have integer entries, that's just a fraction. It's one dot product divided by another. And then we multiply by the length of u. And the picture that you should have in mind for this is, if that's my vector u, and that's my vector v, then the projection takes the tip of v, and we drop down this perpendicular, and we get the projection, right? So there's the projection of v onto u. And the other thing that we've used in the past is that, let me change the color on that. This vector that we have here, this is just v minus the projection of v onto u, and that's always going to be perpendicular to u, right? Or orthogonal, if you like. So you have this idea of orthogonal decomposition. We're actually going to make use of that in one of the eigenvalue problems that we're going to do. Okay, so that's going to come up. I'll show you an example where we actually make use of it. So I'm not just, I'm doing it to remind you because that is stuff that's going to come up. That's the main stuff that we did from Chapter 3. The one thing that I didn't include here that we also did is cross products. But now that you've spent time doing determinants, cross products are a little bit easier if you come back and do cross products. Now that you have those mechanics for determinants down, you can do cross products pretty easily. The one thing I'm not going to do today is all the problems involving lines and planes. If you want to see any of those, please post on the forum. Go onto Piazza and ask for examples with lines and planes, or even better, come up with specific problems, like ones from the textbook or from your homework that you were stuck on, and ask me to do them. And we'll get those done on the forum. Okay, good. All right. So let me go to my first example eigenvalue problem. Okay. Some of these are ones that were in the slides from the last couple of classes, but we didn't always do everything that we could have done with these problems. So I'm going to try and go through all the details for doing these eigenvalue problems. Okay. So that'll be our first example. I'm going to pause for a second. I see my slides have caught up with me. I'm going to take a sip of water. I'm not seeing any questions in the chat yet, but you might be typing. So I'm going to take a sip of water, see if any questions pop up. If not, we'll jump into that first example. I knew there was a question coming. Right. So the question from Cassie is whether there's a difference between cross products and determinants. So there is a big difference, right? Let me go back. Let me actually do something with this. Okay. Let's move that over. Actually, let me just scroll it up a bit. So there are some relationships between cross products and determinants. So I mean, the main thing is, yeah, determinant is something that you do with a matrix, right? So if I give you, say, a matrix like 2, 1, 3, minus 1, 0, 2, 1, minus 1, 4, something like that, and I want to calculate the determinant of A, well, I mean, now we've seen some tricks and techniques for evaluating determinants, right? If I was going to do this determinant, and I wanted to get it done quickly, I would probably add row 1 to row 3, just because adding row 1 to row 3 gets rid of that minus 1 there, right? And then that would simplify. I could expand down column 2. That would be easier. But if we were going to just do cofactor expansion along row 1, remember what this looks like. It looks like, 2 times the determinant 0, 2, minus 1, 4. And then we put that minus sign in, right? Minus 1 times the determinant minus 1, 1, 2, 4. Okay. And then 3 times the determinant minus 1, 0, 1, minus 1, right? Is this my highlighter? No, that's just a drawing tool. What does this thing do? Nothing. It's been a while since I used OneNote. Okay, so the point is that this determinant here, right, that comes from this part right there, right? The middle one is when we delete the second column, we take the outsides. That last one is the first 2 columns. And then, from there we expand those 2 by 2 determinants and we get a number. On the other hand, if I give you, say, V, so let's say I give you V is equal to, I don't know, 1 minus 2, 1, W is equal to 2, 2, 3, I can do the cross product, V cross W, and so the trick we used for the cross product was either this I, J, K along the top, and then we wrote out the first vector, 1, minus 2, 1, then the second vector, 2, 2, 3, right? And then we said, okay, so that's going to be like I times minus 2, 1, 2, 3, minus J times 1, 2, 1, 3, plus K times 1, minus 2, 2, 2. Right? So we can do something like that. Slide that over so my head's not covering it up. Right, and then you expand it out. And so this time, so for the determinant, we get a number, right? We get 2 times 2 minus 1 times that's going to be minus 6, and then we get 3 times 1, so 4 plus 6 plus 3, we get 13 for that determinant. On the other hand, for the cross product, we get a vector, right? That's going to be minus 6 minus 2, so minus 8 minus j times 3, 3 minus 2, 1, k times 2 plus 4, so 6. Right? And we could also write that in vector form. You know, well, maybe we don't want to do angle brackets, right? We'd do minus 8, 1, 6, right? So the cross product gives you a vector rather than a number like the determinant does, but the mechanics of computing the cross product are very similar to the mechanics for computing a determinant. So that's, you know, they're very different things, but they share some kind of similarities in terms of how you compute them. Okay, so the main thing to remember about the cross product is that it gives you a vector, and the significance of that vector is that it's going to be orthogonal to the two vectors that you started with, right? That was the reason that we wanted cross products. In particular, the cross product gives you a normal vector when you're trying to find the equation of a plane. Okay. Okay. So now I'm gonna move on to that first eigenvalue example. Okay. So here's our matrix. We want to find, so all of these problems we're going to find eigenvalues and eigenvectors, and then we're going to see if we can say anything else about it when we're done all of that. Oh, okay, sorry, question from Kat. Let me come back. Where are we? Oh, sorry. It is -1. That's just my mistake. Yeah, there's that minus sign out front. I just dropped the minus sign. So, you're doing all right. That was me, not you. Okay. Thanks for catching that. Eigenvalues. Okay, so remember the basic setup here, the eigenvalue equation, right? Looks like this. A times x is equal to lambda times x. We're trying to solve that equation. We're trying to find a scalar lambda and a vector x that fit that equation for a given matrix. And, oops, sorry. So we said that, okay, this equation here is the same thing as this equation. So this is just a rearrangement of that equation. A minus lambda I times x is equal to 0, right? So this is, it's a homogeneous system. Okay, so it's a homogeneous system of equations, and we want a solution, a non-zero solution. We want a non-zero solution. And if we want a non-zero solution, that means we need the determinant of this matrix to be 0. Okay? And the reason we want that determinant to be 0 is if that determinant is 0, that means the matrix is not invertible. And the only way we can get non-zero solutions to a homogeneous system, if you have n equations and n unknowns, the only way you're going to get a non-zero solution is if the matrix is not invertible. So this determinant condition guarantees that your matrix isn't invertible, which guarantees that you will have non-zero solutions. That's the strategy here. Okay. And so what we do is we first define this characteristic polynomial, right? So the characteristic polynomial is the determinant of x times the identity minus a. Okay, and if you want, you can use the determinant of a minus xi. Okay, it's fine. It doesn't matter which way you do it. It's a matter of kind of personal preference as to which one you find easier to work with. The difference between the two is, well, this one here is arguably easier to set up because all you have to do is subtract x's down the diagonal and then you do the determinant. The main reason why people tend to like putting the x times the identity first is then all your factors, right, when you're dealing with those factors that have the x in them, it's kind of somehow we're used to dealing with, x minus 2, x minus 3, we're used to that, doing 2 minus x and 3 minus x, putting the x on the other side. Sometimes that throws people off when they're doing the algebra. So it doesn't matter which order you put it in because these two determinants, either they're the same or they're off by a minus sign. And so if one of them is equal to 0, so is the other one. So it doesn't matter which way you do it. So do whichever one you find easier, right? Okay. So let's do it. I've set it up this way, so let's go ahead and do it. So what does that determinant look like? Okay. So x minus 2 minus 0 minus 2 minus 0, x minus 2 minus minus 1 minus 1 minus minus 1 becomes plus 1, and then x minus 4. Okay. All right. So I'll do my determinant across the first row. Why not? So I get x minus 2 times x minus 2, 1, 1, x minus 4, 0 in the middle, and then minus 2 times 0, x minus 2, minus 1, and 1. Okay? And now we deal with the 2 by 2 determinants. So I'll come down to here, x minus 2. So we have x minus 2 times x minus 4, subtract 1 times 1, just 1, minus 2 times 0, minus minus becomes plus, x minus 2. Okay, so one of the things that you should be on the lookout for, now this is not something that you should reasonably expect to always happen, but of course I'm going to try to set these up so it works out for you, right? I don't want people to get bogged down in the algebra. If you're doing an eigenvalue problem, whether it's on, let's say, the last web work, the homework 9 on the web work, you're doing eigenvalues, or the final exam once that comes up, or even tutorial 12. If you find yourself with a polynomial that you don't know how to factor, it's okay if you go ahead and you use Wolfram alpha or something and you ask it how to factor the polynomial, right? What I'm looking for when you're doing these problems, I'm looking to see, do you know how to set it up? Do you know what's going on? And I want you to kind of, when you're, especially on the exam, right? The way you convince me that you haven't just put the problem into Wolfram Alpha and copied down the step-by-step solution because you've paid the $5.99 a month to get Wolfram to do your homework for you. The way you convince me that you haven't just copied the thing down from Wolfram Alpha is you explain what you're doing. You say, okay, well, I know that I need to set up the characteristic polynomial. It looks like this. I'm going to expand the determinant. I'm going to try to factor. You tell me what you're doing as you do it. Explain your thought process. That's what I'm looking to see is kind of that, what are you thinking about? But one of the things that you should be looking for once you've expanded that determinant is, do you have this kind of group factoring set up, right? Once you get rid of that plus 0, right, you have x minus 2 as a common factor for both. I will try to set things up so that you always have sort of that common factor you can take out. I don't want you to be bogged down on trying to factor a cubic and doing long division and things like that, because that just gets gross. So what do we have? Pull out the x minus 2. In that first factor, I've got, so if I multiply that out, x squared minus 2x minus 4x. X squared minus 6x plus 8 minus 1, and then I have the minus 2. Okay? That's this minus 2 right here. Okay? So altogether, 8 minus 1 minus 2 That's 5. Okay, so I have x minus 2, x minus 1, x minus 5. Okay, and so the eigenvalues, the lambdas, are going to be the numbers that you plug into that polynomial to get 0. So it's going to work for lambda is equal to 1, 2, and 5. Those are your eigenvalues. Okay. Once you find the eigenvalues, now it's up to finding the eigenvectors. And so for the eigenvectors, we return to this equation up here, but we sub in the particular values of lambda that we've found. Okay, so let me scroll down and show you what that looks like. So let's do lambda is equal to 1. Okay, so a minus lambda I, in this case, just becomes a minus I. Okay, and I've got a written down, so this is going to be, so here's a. So a was 2, 0, 2, 0, 2, minus 1, 1, minus 1, 4. And now we subtract 1, right? Minus I, we have those 1s down the diagonal, like so. So we get 1, 0, 2, 0, 1, minus 1, 1, minus 1, 3. Okay, so there's our matrix. Okay, and so we're trying to solve. Remember what we're trying to solve. We're trying to solve this equation: a minus I times x is equal to 0, where x is, say, x1, x2, x3. Okay. All right. So it's up to you when you're setting these things up. Because it's a homogeneous system, right? If you want to write the augmented matrix, 1, 0, 2, 0, 1, minus 1, 1, minus 1, 3. If it helps you keep track of what's going on, put the column of zeros on the right-hand side. A lot of people, when you're doing everything in the context of homogeneous systems, a lot of people don't bother to put the zeros because you're just carrying that column of zeros along the whole way, and it's extra writing that you might feel you don't want to do. But let's put it. Okay. So what are our row operations going to be? Well, let's get rid of. So we're going to do row 3 minus row 1 into row 3 because we want to create a 0 in this spot here. 1, 0, 2, 0, 1, minus 1, and then we get 0, minus 1, 1. 0, 0, 0. Okay. And so now we can do row 3 plus row 2 into row 3. 1, 0, 2, 1, minus 1, 0, 0, 0. Okay? And you should always get that row of zeros on the bottom, right? You should always have at least one free variable, right? The whole point is that when we subtracted off lambda times I, right? If lambda is an eigenvalue, when we subtract off that multiple of the identity, the whole point is we're making a matrix which is not invertible, right? And if the matrix is not invertible, then we must have at least one column that doesn't get a leading 1, right? There has to be at least one free variable. So if you're getting down to reducer echelon form, and let's say that you get it down to reducer echelon form and you find that you actually get a leading 1 in that spot, so there's leading 1 all the way down. Well, then something has gone wrong. And so there's two possible mistakes that you might have made. Maybe you made a mistake doing the row operations, right? Or you made a mistake finding the eigenvalues, but somewhere along the way you made a mistake. So you have to have at least one free variable, otherwise something went wrong. Okay, so that's our reducer echelon form. And what are those two rows? What do they tell us, right? Those two equations that we have there. The first one says x1 plus 2x3 is equal to 0. The second row says x2 minus x3 is equal to 0, right? So that means that x1 is minus 2x3, x2 is equal to x3, x3 is free. Okay? And so that means that my vector x looks like this. It looks like minus 2x3, x3, x3. Okay? So x3 times minus 2, 1, 1. And so typically what we do, we'll get to that, Mitch. Yeah, so Mitch is asking you, what if you have two free variables? We'll do an example with two free variables. It's coming up. That shouldn't happen unless you have a repeated eigenvalue. The only way you could possibly get two free variables is if you have a repeated eigenvalue. And if you have two free variables, that just means you get two eigenvectors corresponding to that particular eigenvalue. We will definitely do an example like that. So it's coming. It's coming. When you have all distinct eigenvalues like this, we get three different eigenvalues. Each eigenvalue should come with one eigenvector. Okay. So at this point, we're kind of done. We're done with the first one. What we do is we typically want the basic solution. So remember, the basic solution is the one where you just set the parameter equal to 1. So in this case, that minus 2, 1, 1, that's going to be our first eigenvector. That's the eigenvector corresponding to lambda equals 1. If you have a problem that's asking you for a unit eigenvector, that can happen. Well, we talked about that in that kind of review at the beginning. You can just, what's the magnitude of this one? 4 plus 1 plus 1, right? So that vector has magnitude 6. So if you or root 6, right? So if you multiply by 1 over root 6, you would have the corresponding unit vector. But if you don't need unit vectors, it's nice to have integer entries, right? So we'll just leave it as minus 2, 1, 1. That's our first eigenvector. So now we'll do the next one, okay? So the next one up is lambda is equal to 2, okay? So this time I'm going to do a minus 2 times the identity. So we start with a, 2, 0, 2, 0, 2, minus 1, 1, minus 1, 4. And now we're going to subtract 2 off the diagonal. So we get 0, 0, 2, 0, 0, minus 1, 1, minus 1, 2. Okay. Okay. Oh, sorry. So Cassie asked about the 6. So all I'm saying is, so this, for that first one, right? So the first vector, we're going to, ultimately the vector that we end up taking, our answer is going to be this, right? Minus 2, 1, 1. And probably that's the answer that you're going to go with, because we like integer entries. But if you needed a unit vector, you could calculate the magnitude of x, right? The magnitude of x would be the square root of minus 2 squared plus 1 squared plus 1 squared. So that's 4 plus 1 plus 1. So you get root 6. So if you needed a unit vector for some reason, you would multiply by 1 over root 6 to get a vector of length 1. But we don't need unit vectors for this problem, so I'm going to leave it as it is. So minus 2, 1, 1. That's our vector. Okay. Okay. Now, for this next one, I'm going to, if it's all right with all of you, I'm going to jump straight to the reducer echelon form. Okay, for the second one, for lambda is equal to 2. All right, so how did I get to that reducer echelon form? Just what would be the steps if you wanted to do it? Well, I would take that bottom row, move it up to the top, right? And then that middle row multiply by -1 to get the leading one in the third column. Use that leading one in the third column to make zeros above and below. Now you're in reducer echelon form. A lot of the time it will be pretty simple getting these matrices into reducer echelon form. So if you can jump straight to reducer echelon form, feel free, okay? So what does this one say? So I'm going to take, this time, maybe I'll call my vector y this time. y1, y2, y3, okay? So that first row says y1 minus y2 is equal to 0. The second row says that y3 is equal to 0, right? So this time y2 is the free variable, and my vector y. So y1 is equal to y2, so I get y2, y2, and 0, or just y2. Sorry, I'll move that over. Times 1, 1, 0. Okay. Okay. So there's my second eigenvector, right? So what we're going to do, again, we won't worry about unit vector. This vector, if we wanted to, right, the length of that vector is square root of 2, 1 squared plus 1 squared. But we're not worried about unit vectors, so we just leave it as that. So there's our basic solution for the second homogeneous system. Notice this time I didn't bother putting that column of zeros. It gets annoying to write it. It's just zeros, right? So there's the answer. So I'm going to put it over here. So my second eigenvector, 1, 1, 0. Okay? So there's my second one. Okay? And what was my last eigenvalue? 5. So let's go and we'll do that last one. So lambda is equal to 5. Okay? So for lambda equals 5 eigenvalue, a minus 5 I. So we're going to get 2 minus 5, 0, 2, 0, 2 minus 5, minus 1, 1, minus 1, 4, minus 5. So minus 3, 0, 2, 0, minus 3, minus 1, 1, minus 1, minus 1. Okay, oh, question in from Joseph. Y2 is free. The reason Y2 is free for lambda equals 2 is because there's no leading one in this column, right? The way you know what your free variables are is you look for the columns that have leading ones. There's no leading one in the Y2 column. The Y1 column has a leading one there. The Y3 column has a leading one there. Y2 is free because there's no leading one in its column. Okay. Yeah. So remember, when you're looking for number of free variables and deciding which variables are free, you're looking at columns with and without leading ones. And that's going back to chapter 4, when we're just standard techniques for solving systems, which is one of the things that you'll want to kind of brush up on as we're heading in towards the exam. Right. Okay, so we got to reduce that matrix, right? So probably what I'm going to do for this matrix is I think we want to swap row 1 and row 3. 1, minus 1, minus 1, 0, minus 3, minus 1, minus 3, 0, 2. Then we're going to take row 3 and we're going to add 3 row 1. So we have 1, minus 1, minus 1, 0, minus 3, minus 1. So that's going to be 0, 3, and hang on. Oh, sorry, 0 minus 3, because we're adding, minus 1. Okay. And so you'll notice that you get two rows that are the same, right? So we're gonna do 2 more row operations. We're gonna do row 3 minus row 2 into row 3, 0 minus 3 minus 1, 0, 0, 0. Having done that row operation, I've just, these are one of these ones where sometimes you kind of do 2 steps at once. Be careful about doing 2 steps at once. I'm going to do this row operation as well. I'm going to divide row 2 by minus 3, get my leading 1, okay? So that means that's going to become a 1. Oops, let's go back to black pen. 1 and 1/3. And 1 step to go. Okay, last thing we want to do is row 1 plus row 2 into row 1, 1, 0. So minus 1 plus 1/3 gets me to minus 2/3, 0, 1, 1/3, 0, 0, 0. Okay, so that one took a little bit more work than the other ones, but we got there in the end. So let me slide that up. So we need one more eigenvector. So I'm going to let Z be Z1, Z2, Z3. And so if A minus 5I times Z, if that's equal to 0, right, that homogeneous system, well, looking at the equations that we have here, we're going to get Z1 minus 2 over 3 Z3 is equal to 0. Z2 plus 1 over 3 Z3 is equal to 0. So this time what we get is Z1 is 2/3 Z3. Z2 is equal to minus 1/3 Z3. Z3 is free. Okay. So what I'm going to do is I'm going to choose. I can choose any value I want for Z3, except 0, right? Because 0 would give me the 0 vector, and I don't want the 0 vector. I'm going to choose Z3 equal to 3. Why? I want to get rid of the fractions. If I multiply 2/3 by 3 and I multiply minus 1/3 by 3, I get rid of the fractions. And if I do that, then here is my final eigenvector. Minus 2, or 2, minus 1, and 3. Okay? So at this point we found all 3 eigenvalues, we found all 3 eigenvectors corresponding to those eigenvalues, right? There's a lot of work in one of these problems, right? It's right, we're already kind of halfway through the video. We've done our first example, so we might have to pick up the pace a little bit here. But I want to show you one more thing. One more thing before we move on. One of the things that you might notice is that if we let P, so P is going to be a matrix where we put X in the first row, or first column, Y in the second column, Z in the third column. Okay? So let's go all the way back up. What was X? Minus 2, 1, 1. Y was 1, 1, 0. Z is 2, minus 1, and 3. Okay? So what I want to show you is that if you do A times P, well, A times P is going to give you, it's going to be AX, AY, AZ, z. Right? You can kind of do this this block multiplication like that when you're doing matrix multiplication. But remember that x was an eigenvector corresponding to the eigenvalue of 1. So we should just get x there. Y was an eigenvector corresponding to the eigenvalue 2. So we should expect to see 2y. Okay? Z had eigenvalue 5, so we should expect to see 5z. Let's check. Okay? Here's A. 2, 0, 2, 0, 2, minus 1, 1, minus 1, 4. Okay? And here's P. Okay? I'm going to multiply those together. Let's see what I get. Okay, so what I'm going to get, I'm going to do the multiplication, all right? You can trust me in this because I want to be able to move on to the next one. Minus 4 plus 2 is minus 2. Moving on, row 1, column two, row 1 of A times column 2 of P, I get 2. Then I get 4. 4 plus 6 is 10. Okay, and then I'm moving on to the middle row. 2 minus 1 is 1. 2 minus 2 minus 3 is minus 5. And then down to the last row, I get minus 2 minus 1 plus 4 is 1. 1 minus 1, 0. And then finally, I get 2 plus 1 is 3 plus 12 is 15. Okay? And notice that it works, right? That's exactly what I expect to get. All right, this one here is, that row is x, that's 2y, that is 5z. It does what I'm supposed to do. Okay? Yeah. Oh yeah, and so the question from Sarah, you can, yeah, so it doesn't matter what scalar multiple you choose to put in, right? One of the things I think on the last video, one of the things that we showed is that, or maybe this was in the very first class that we did on eigenvalues and eigenvectors. If you have one eigenvector, then any scalar multiple of that eigenvector is still an eigenvector with the same eigenvalue. So if I wanted to, if I replaced, let's say I decided to make, maybe I decided that this would be 2, 2, 0 for some reason. I wanted to double that column. Well, then I would have 4, 4, 0 at the end, right? It would still get doubled, right? So the numbers you get out at the end might change, but the relationship is still going to be the same. And the last thing, which I'm not going to do because it's time consuming and I got half an hour left and I want to do a couple more of these examples. Here's the exercise. The first thing I want you to do is find P inverse. Find the inverse of this matrix P that we just constructed. The second thing I want you to do is confirm the following. Confirm that if I do P inverse times AP, right, and we just found A times P, when you do P inverse times A times P, you will get this. Okay, you'll get a diagonal matrix with the eigenvalues down the diagonal. Okay, so I'm gonna skip that step just because finding inverses is annoying, and my tablet doesn't. I don't have the keyboard attached. I'd say it's perfectly fair game. By the way, if you have a diagonalization problem on the exam or in your homework, when it comes to the step of finding the inverse, right? Maybe there's a separate problem where I'm actually going to ask you to find the inverse using, showing all the process. But if computing the inverse is just one step in a multi-step problem like this, right, and there's a lot of steps, I think it's perfectly acceptable at this stage in the game to use software to find that inverse, right? There's lots of computer programs that will find the inverse of a matrix for you. So you could ask the computer to do the inverse and then check that it works out. But it's also good practice to do it by hand, so I'm going to let you give it a try. See if you can get it to work out. Okay, well, that was a bit of a marathon, right? And that's only one example. Let's see how the next one goes. All right. I was thinking, oh yeah, we can do 5 examples, right? Like 15 minutes a problem. That's, yeah, easy. No, not gonna happen. Okay. Let me do this next one. Okay. Show you what happens. So in this one, and I'm gonna go a little bit faster on this one, if you guys don't mind, because I wanna get through at least 3 of these before we quit. So for this one, let's do the characteristic polynomial. So characteristic polynomial, okay, we're going to get x minus 2, 0, 0, 2, x plus 2, minus 2, 5, 10, x minus 7. Okay, so those zeros on the top are nice because it means I only have this one 2 by 2 to worry about. So I'm going to get x squared minus 5x minus 14 plus 20. So I'm going to get x minus 2 times x squared minus 5x plus 6. So that's x minus 2 times x minus 2 times x minus 3. All right. So this time, my eigenvalues are lambda is equal to 2 and lambda is equal to 3. And for that lambda is equal to 2, what we would say is we say that one has so-called multiplicity of 2, right? Because lambda or x minus 2 shows up twice in the characteristic polynomial. Okay? So what happens when we go looking for the eigenvectors corresponding to that eigenvalue? Well, let's find out. If I do a minus 2I, okay, I'm going to get 2 minus 2, 0, 0, minus 2, minus 2, minus 2, minus 2. Oh, what am I doing? Not there. And then, sorry, 2 minus 5 minus 10 and 7 minus 2. Subtract 2 down the diagonal. So I get this. I get 0, 0, 0. Then I have minus 2, minus 4, 2, minus 5, minus 10, and 5. So what I want you to notice is that, and let me jump straight to reducer echelon form here. One of the rows is already 0, and the other two rows are both multiples of 1, 2, minus 1, right? The second row, I take 1, 2, minus 1. The second row, if I multiply by minus 2, that gives me the minus 2, minus 4, and 2. If I multiply by minus 5, I get the minus 5, minus 10, 5. Okay? So this time I get 2 rows of zeros. I only have one leading 1, right? 2 free variables. Okay? So if I have, say, x equal to x1, x2, x3, and if x is a vector so that a minus 2I times x is equal to 0, well, what does that mean? That means that x will look like, right? So that row just says that x1 plus 2x2 minus x3 is 0. x2 and x3 are both free. So solving for x1, I get minus 2x2 plus x3. x2 is just x2. x3 is just x3. So this is now kind of answering Mitch's question from a while ago. What do? Well, you break this up, right? We've done this when we're solving homogeneous systems. We get x2 times minus 2, 1, 0. x3 times 1, 0, 1. Right? So that first vector is just coming from, the minus 2x2 from there, the 1x2 from there, and there's 0x2 in the third row, right? The other one comes from the 1x3 from here, and then 0x3 in the middle, and then 1x3 at the end, yeah? So we get two basic solutions to the homogeneous system. Those are two independent eigenvectors, right? Neither one of those vectors is a multiple of the other, so they are two separate vectors, right? So we might refer to these as maybe, say, vector x1, vector x2, right? These are, so we get two eigenvectors with eigenvalue lambda is equal to 2. Okay? And now if we wanted to, we can also do the lambda is equal to 3, and we can go from there. So I want to show you a couple more examples. So I'm going to leave this one. I'm going to leave the lambda equals 3 as an exercise. But I want to emphasize that from here on out, everything kind of looks the same as before, right? If you follow, you can follow the previous example in the same way. You know what? Actually, no. I have time. Let's do it. I have 20 minutes. We can do it. Let me show you how it works. We'll still be able to get another example in. So for lambda equals 3, a minus 3i. So I get 2 minus 3, 0, 0, minus 2, minus 2, minus 3, 2, minus 5, minus 10, 7, minus 3. Okay? So I get minus 1, 0, 0, minus 2, minus 5, 2, minus 5, minus 10, 4. Okay? So first thing I'm going to do here, right, if I'm trying to get down to reducer echelon form in this thing, well, I'm probably going to change that minus 1 to a plus 1, go to 1, 0, 0. Then I'm going to use that leading 1 to get rid of the minus 2 and the minus 5, right? I want to get rid of these. But here's the thing, because I have zeros there, I can just delete the 2 and the minus 2 and the 5. Those go to 0, and the other entries, they don't change. Right? Because I'm adding 0. And now you notice that row 3 is just twice row 2. So we are going to get that row of zeros on the bottom. And the only other thing left to do to get into reducer echelon form is divide row 2 by minus 5. Okay, so there's your reducer echelon form. If y is, say, y1, y2, y3, I'm just using a different letter so I don't confuse it with the vector that I had for lambda equal to 2. So if I have that y, and if I have a minus 3i times y is equal to 0, well, then that reducer echelon form tells me, well, that first row says that y1 has to be 0, right? y1 plus 0 is equal to 0. The second row says that y2 is 2 over 5 times y3. Okay? So I'm going to take y3 to be equal to 5. Because I don't want a fraction. If I take y3 equal to 5, my other eigenvector is going to be 0. 2 over 5 times 5 is 2, and then y3 is 5. 0, 2, 5. Okay? So I get that one eigenvector corresponding to the eigenvalue of 3. If we wanted to diagonalize, and I'm not going to do the whole thing, but just to tell you where you would start. So let's say we want to diagonalize. I'm going to take P to be. So the first two columns of P are going to be those two basic eigenvectors that I found corresponding to the lambda is equal to 2. So the minus 2, 1, 0, and the 1, 0, 1. 1, 0, 1. And the third column is going to be that eigenvector that I just found, the 0, 2, 5. And what you can check is that if I do, and again, I'm not going to do this work, if I do P inverse times A times P, I should get 2, 0, 0, 0, 2, 0, because those first two vectors both had eigenvalue 2, and the third vector has eigenvalue 3. And by the way, if you're wondering about like ordering, like what if you put the lambda 3 equals 3 eigenvector first? What if you put that 0, 2, 5 as the first column? Well, all that happens if you rearrange the columns is you rearrange the order in which those eigenvalues are going to appear on the diagonal. So if I had put the 0, 2, 5 eigenvector as the first column, when I diagonalize, my diagonal matrix would go 3, 2, 2 instead of 2, 2, 3. Right? Okay. I think we're doing all right. I've got 15 minutes. We can do one more example. I've got two that I'm going to skip. I'll try to do videos, like kind of standalone videos for the two that I'm not doing right now. I'm going to do one more, and it's one that we already did, but I want to kind of go a little bit further than we did the first time around. Okay. One of the videos I'll do for you later is showing what happens if you have a repeated eigenvalue but you don't get two eigenvectors corresponding to it. Basically, you can't diagonalize in that case. And we live with that. That's fine. We can live with it. Let me do this as the last example before we go. Okay. We did this one already, but let me show you what happens. Okay. So find the characteristic polynomial. X minus 1 minus 1, x minus 1 minus 1, x. So x times x minus 1 minus 1x minus 1 times minus 1 minus 1 minus 1 x minus 1 times minus 1x minus 1 minus 1. Okay, so this is going to be x times x squared minus 1 plus minus x minus 1 minus 1 plus x. So this is going to be x times x minus 1 times x plus 1 minus x plus 1 minus another one. So actually minus 2x plus 1. Okay, and so again, notice that we have a common factor. We can take that out. X plus 1 times x minus 1 minus 2. X squared minus x minus 2. Okay. So that is going to be, once you factor all out, x plus 1 squared times x minus 2. Okay, so eigenvalues are going to be lambda is equal to -1, and that one has a multiplicity of 2, and lambda is equal to 2. All right. Now, one of the other things I want to point out here before we move on, I want you to notice one thing. This particular matrix is symmetric. A transpose equals A. Turns out symmetric matrices have really nice properties when it comes to diagonalization. I'm going to try to spell those out in the 12 minutes we have left. Okay? So let me do the lambda is equal to 2 eigenvalue first. Okay? So A minus 2I will look like this. Okay? Minus 2, 1, 1, 1, minus 2, 1, 1, 1, minus 2. There it is. So I'm going to, let's see. Let me swap row 1 and row 2. Okay. And now let me create some zeros. 1, minus 2, 1. So double row 1 and add it to row 2. 0. 1 minus 4 gives me minus 3. 1 plus 2 gives me 3. And then I'm going to subtract row 1 from row 3. 0, 3, minus 3. Okay? I'm going to do 2 row operations at once here. 1, minus 2, 1, 0, 1, minus 1. We can see that that third row is going to cancel, right? Okay. One more step to get to reducer echelon form. I'm going to do row 1 plus 2 row 2 into row 1. It's my last one. 1, 0, minus 1, 0, 1, minus 1, and then 0, 0, 0. Okay? All right. And so if I had A minus 2I times x is equal to 0, where x is, say, x1, x2, and x3, then we can see that what we got to have here is x1 minus x3 is equal to 0, so x1 is equal to x3, x2 minus x3 equals 0, so x2 is equal to x3, and that means that x is, so if I put x3, so x3 is free, I'm going to put it equal to 1. 1, 1, 1. Okay, I'm going to leave it at that for now. Okay, now let me do the lambda is equal to minus 1 eigenvalue. Okay, so A minus 1 I becomes A plus I. Well, this is just 1, 1, 1, 1, 1, 1, 1, 1, 1. Well, pretty easy to see what reducer echelon form is here. Right? So if A plus I times y is equal to 0, and y looks like, say, y1, y2, y3, well, then we get that y1 has to be minus y2 minus y3, right? Because y1 plus y2 plus y3 has to be 0. So that means that y is going to be minus y2 minus y3, y2, y3. So I get y2 times minus 1, 0, minus 1, 1, 0, y3 times minus 1, 0, 1. Okay, so I get this vector and that vector. So maybe I'll call this one, let's give these new names. Let's call this one maybe V and W. Okay. Okay. Somebody wants me to go back. Let me head back up. Are we going all the way back up to here? So let me just, let me throw in, just to remind you, the original matrix was 0, 1, 1. Right? So if I subtract 2 times the identity, I'm putting minus 2's down the diagonal. Right? So I get down to reducer echelon form, and here's my reducer echelon form. Okay, and once I've got that reducer echelon form, right, the first row says that x1 has to equal x3. The second row says x2 has to equal x3. So my eigenvector is going to be any vector where all 3 entries are the same, and I chose to set all 3 of them equal to 1. Now, for the lambda is equal to minus 1, right? Minus 1 becomes plus 1. So if I add the identity matrix, right, which has 1's down the diagonal and everywhere else, if I add the identity matrix, I'm going to be putting 1's in those spots. Okay? So that gets me to this matrix here. And so if I take row 1 and I subtract it from row 2 and from row 3, that gets me to here. So y1 plus y2 plus y3 has to be 0. That's what that first row says. Right? The 3 entries have to add to 0. And I can solve that equation for y1. So I'm going to take y2 minus y3 and I plug it in for y1. And then it's this usual kind of decomposition game that we play. The first vector is the minus y2, and then there's 0 y2 in that third spot, right? And that second vector is the minus y3, no y3 there, and a y3, and I'm factoring out. Let me know if that's all right. I'll take a short break. We got 5 minutes. Yeah, we can get it done in 5. Maybe 6. Are we okay? Let me know if we're okay. Okay. So I wanna point out what we've got here. Okay. So we have, these are the vectors that we have. Okay. We've got x, equal to 1, 1, 1. We've got v equal to minus 1, 1, 0. And I've got w equal to minus 1, 0, 1. Okay. So this here, this is my lambda is equal to 2 eigenvector. And these ones are both lambda equals minus 1. One of the things I want you to notice is that if I do x dotted with v, I get 0. And if I do x dotted with w, I get 0. But v dotted with w is equal to 1, not 0. Okay. Turns out there's a theorem that for a symmetric matrix, eigenvectors coming from different eigenvalues are always orthogonal. Okay. But if you have 2 eigenvectors coming from the same eigenvalue, they're typically not orthogonal. But here's the cool thing. So here's the note we want to make. Any linear combination of u and, v, I call it v, and w is also an eigenvector for lambda equals minus 1. Okay? Now, I'm telling you this for a reason. It would be really nice if all three of these vectors were mutually orthogonal. Okay? So far only 2 out of the 3 are. But here's what we can do. I'm going to calculate the projection of W onto V. V dot W over V dot V times V. So V dot W is 1. We just calculated that. V dot V is 2. Minus 1, 1, 0. So I get minus a half, and 0. And now I'm going to let U be W minus the projection of W onto V. Okay? So minus 1, 0, 1, subtract. Minus a half, 0, gets me to minus a half, and 1. Now, I want you to check that that's still an eigenvector, okay? But now notice that I'm going to use x, still going to be 1, 1, 1. I'm going to use v, which is minus 1, 1, 0. And instead of w, I'm going to use this u. Minus a half, and 1. And we could write that as that's minus 1/2 times the vector 1, 1, minus 2. Okay? Now, what I want you to check is that x dot v is 0, x dot u is 0, and u dot v is also 0. And x is still an eigenvector with eigenvalue 2. U and v are still eigenvectors with eigenvalue minus 1. I'm going to let you check that, okay? So, what can we do with this? Well, what I'm going to do now is I'm going to get unit vectors. So let's give them some new names. Maybe I'll call them A. So A is going to be the unit vector in the direction of x. X has length root 3. B is going to be unit vector in the direction of v. 1 over root 2. C is going to be a unit vector in the direction of u. Now, if I ignore the minus 1/2 out front, let's see. U, that's going to be 4, so C is going to be this, 1 over root 6. Now, I'm going a little bit fast because I'm a minute over time. I want you to check that these are all actually unit vectors. I want you to check that they're still all orthogonal. And I want you to let P be this vector. 1 over root 3, 1 over root 3, 1 over root 3. So A in the first column, minus 1 over root 2, 1 over root 2, 0, and then 1 over root 6, 1 over root 6, minus 2 over root 6. Okay? And I want you to check something. I have to leave you to do this because we're out of time. I want you to check that P times P transpose is the identity. So that means that P transpose is actually inverse. And I also want you to check that if you do P transpose times the original matrix A times P, you're going to get 2, 0, 0, 0, minus 1, 0, 0, 0, minus 1. So you can diagonalize. So this this matrix that we have here, this is an example of what's called an orthogonal matrix, right? And it's nice to have an orthogonal matrix because obviously transpose is a lot easier than inverse, right? Transposes are easy to do. So this is something that people use quite frequently. There are a lot of computational problems where diagonalizing a symmetric matrix is a key step in the process, right? And you want to do this orthogonal diagonalization. You want to find not just any old eigenvectors, you want to find eigenvectors that form what's called, so these ABC, they form what's called an orthonormal basis, okay? If you dot any of those vectors with itself, you get 1. If you dot any two different vectors together, you get 0. So these, they're kind of like, you know, in a way, it's a lot like I, J, and K. They have a lot of the same properties as those vectors I, J, K in terms of how you work with them computationally. Okay, I'm under time. Actually, I'm 4 minutes over time. My kid's probably upstairs in bed waiting for me to come read him a book. I'm going to pause for 1 minute just to see if anyone has a last question they got to throw at me. And if not, that's a wrap. I'll try to do a few more. Like I said, I'll do a couple of kind of pre-recorded videos that I'll throw up on YouTube for you to watch. We'll do a couple more eigenvalue examples. Keep getting at me at the forum. Over the weekend, I'm going to relax a little bit because I need to sleep. At this point, I need to sleep. Starting next week, I'll put up some more hours you can use to book me for office hours. The good news is we got lots of time until the final. The final is after Easter, I think. We got a little bit of a breathing room before the final exam. So you got lots of time to get at me with questions. You can book me for Zoom meetings if you want to meet with me face-to-face and go over some stuff. We'll set that up on Moodle again. You can book me for Zoom meetings. And otherwise, throw your questions on Piazza, and either I will answer them or Sean Legg will answer them. We'll both get at that as soon as we can. All right. I stalled a bit for more questions. I'm not seeing any. So I'm gonna end our stream here. And thanks everyone for bearing with me. And yeah, I could try to trim. I'll see how it goes. I'll see what I can do. I'll have a couple other videos doing similar stuff. We'll this, you know what? I might even already have this. Let me go check out the videos I already have. There might even be one like this already. I feel like this is an example I like to do. So go take a look. I might already have this as a video. The ones that I did like a few years ago. Go check and have a look. I'll have a look. It won't be right now, but I'll check and I'll let you know if I find it. Okay. Thanks for tuning in, everyone. I'll talk to you on the forum.